Hey, good morning, everyone. Before we get started, do you have any question? Okay, so next.
Professor, I have a question, just real
Definitely.
fast. I sent you an email
Okay.
about something weird happened to what I sent in. Did you receive it?
You mean the email? Yeah, I didn't check today, but I think I received an email. Yeah, hold on.
Okay, thank
Okay.
you.
Yeah. Okay, no problem. Yeah, so I'll look into that while you work on your Excel project, right? Yep. Okay. So next Monday, we will review for the midterm exam. So when you come back from the spring break, you take the exam number one. I mean, the midterm exam. Yeah. Yeah, that's right. Okay. Any other questions? Okay. All right. Feel free to stop me if you have any question. All right. So we're going to continue from last week. And we talk about the chapter 5 on the discrete probability distribution and some of the applications in the real world. And then we're gonna talk about couple more important concepts. One of them is called expected value. So we're still on chapter 5. Discrete PT distribution. Oh, by the way, for the midterm, right? Midterm covers chapter 1 all the way to 5, right? Chapter 1 to 5. We may start on chapter 6, but it's not going to be on the midterm. So chapter 6, and after that will be on the final exam. Okay. All right, so let's talk about the expected value. So expected value is very important concept in any investment activity. If you have any investment or gambling activity, right? Or if you go to casino, play any game, and this concept, it's kind of important to guide you, in terms of winning or losing when you play those games. So expected value basically saying that represent the average value of the outcomes, right? So expected value is average value of all the outcomes. It's sort of like weighted average, but the weight here is probability, right? So we look at probability in terms of weight. Okay, so now let's think about this, right? Let me give you an example. Now you understand what this is about. Let's say we playing New Jersey Pick 3 game. All right, so you're betting, let's say 50 cents. And then select 3-digit number. Ranging from 000 to 999. Okay. If you hit a number, and you collect say $300. And here the hidden information is net gain, right? Because remember you betting 50 cents and then the 50 cents is gone. So it should be deducted from the final payout, right? $300. So net gain here is $299.50. Okay, so this is an important piece of information. Keep that in mind. And suppose you bet 50 cents, right? So you're picking a number on number. $0.007. Okay. And what is your expected value of the gain or loss? What is expected value? So now, so we need to think about this whole situation here. So this New Jersey Pick 3 gain has from 000 to 999, right? So that should be 1,000 numbers. The way how you determine how many numbers are there, you just using 999 minus 000, ending number minus beginning number, adding 1. Okay, so this is total number available to pick. Right, so we end up with 1,000 numbers in between. So we have 1,000 numbers, and I remember there's only one winning number. So probability of winning would be 1 over 1,000. Probability of losing would be 999 over 1,000. So that is also important. So now let's take a look at this. Usually for all this expected value, probably you can solve using a table. Okay, so basically we have two outcomes, right? Should be outcomes. You look at the outcome here, only two outcomes, either you win or lose. Okay. Outcomes, win or lose. And then when you win, so let's look at the monetary reward, right? If you win, okay, actually I forget to show you guys the formula for the expected value. Expected value is using this mu of x. So it's like expected value of the discrete random variable x. It's the average return or average value of all the discrete random variable, all outcomes. And this is summation of x times p of x. And p of x definitely is probability of x. X here is usually for the investment activity or gambling activity, meaning monetary reward or your monetary loss, right? So that basically appear in two different outcomes. If you win, you have a net gain, right? So winning case, we have a net gain. Remember, you're getting $300, you're betting 50 cents. So the net gain is $299.50. So here we put a net gain of $299.50. So this extra represent, in the winning case, represent a monetary reward, right? And in the losing case, you end up with a net loss. And net loss here will be 50 cents, right? Remember, you betting 50 cents. All you can lose is 50 cents. So it's minus, since it's loss, it's minus. It's like deducting from your checking account or something like that. So minus 50 cents. Now you look into the probability associated with each outcome, P of X. So as I mentioned earlier, there's 1,000 numbers. Only one number is winning number. So the probability of winning will be 1 over 1,000. Okay. So this turning to decimal will be 0.001. Okay. And there are 999 losing numbers. So the probability of losing will be 999 over 1,000. So this turned out to be 0.999. So again, they are complement, right? You either win or you lose. There are only two cases, two outcomes available here. There's no between, right? No like neutral, anything like that. So, and then all we have to do is multiplying the monetary reward or loss by the associated probability. So x times p of x. So it's like weighted average based on the probability, right, of all those outcomes. So 299.50 times 0.001, and it becomes positive 0.2995. Okay, yeah, so that would be, yeah, you multiply this two. Yeah. And if you multiply negative 0.50 by 0.999, let's see what that is. Now that turned out to be 0.4995 negative. Okay. And if you combine those two outcomes, right, associated with probability, then we get an expected value. So expected value, in this case, it's total of that x times p of x. So you just sum up those two numbers. So you end up with a negative 0.4995 adding 0.2995. And the result of this is negative 0.20. So what this tells us is, in terms of interpreting this outcome here, or this result will be on average, every time you play usually pick 3 game, you expect to lose 20 cents on a 50 cents bet, right? $0.20. So this basically is an interpretation of this expected value. And it's quite useful in terms of making decision on an investment activity or any gambling activity. If you feel like it's not a good game to play, it's not worth to play, then you just drop it, right? But if you feel like, it's not too bad, on a 50 cents bet, you only lose 20 cents, but still, when you win $300, right? That the payout is compared to your bet is pretty high. And that's usually the key characteristics of all those lottery games, right? Usually your payout is very, very high, right? If you play in the New York Mega Million or lottery game, right? The payout it's very high, but the associated probability is very, very, very low. So that's why actually we went over one of the calculation about calculating the probability of winning that Mega Million, right? So very similar case. Just look at the probability with the associate monetary reward if you win, and monetary loss if you lose. Now you'll be able to find out the expected value, even for if you play the Mega Million or any lottery game. Okay. Any question on this expected value? So the key thing is figure out the reward and then the loss, right? And then after that, find out the associated probability. Then you just multiply them. And eventually, sum up those two products, and you end up with the expected value. Okay, so this is another important concept in chapter 5. And the last one I want to talk about in chapter 5 is called binomial probability distribution. Binomial probability distribution. So now let me give you a very simple example. Let's say you flip coin 5 times. And you count number of heads. It's just assuming you're betting on the heads, right? So you're counting how many heads show up when you flip coin 5 times. And this is exactly the concept of binomial probability distribution. And there are some key aspect in terms of looking at this distribution. First of all, if you look at it carefully, when you flip coin 5 times, right? Each procedure has 2 outcomes, right? So if you look at flip a coin 1 time as a procedure, then each procedure has 2 specific outcomes, right? Has 2 outcomes, or outcomes in 2 categories in this case, or outcomes in 2 categories. In this case, you either get a head or tail. So you have either head or tail. Secondly, the procedure have fixed number of trials. So here, if you look at the entire, we flip a coin 5 times. So the fixed number of trials here will be 5. So procedure has a fixed number of trials. In this case, it's 5 trials, meaning when you flip the coin 5 times, it's 5 trials. And then the third important aspect is that the trials are independent. How do we know that? Because when you flip a coin 5 times, you never, the outcome is not guaranteed. So you either have a head or tail, right? But it's not guaranteed. This is 50% chance. So that's why that makes sure that all these trials are independent. 50% chance on each outcome. And then also the probability of success or probability of failure or probability of head and probability of tails here remain constant. So the probabilities must remain constant for each trial. Meaning probability of success, or probability of head or probability of tail here remain constant. They are both 50%. And here, if let's say we betting on heads, we could assuming getting ahead is a success event. So in this case, more broadly speaking, you can just look at outcomes in 2 categories, either success or failure, right? Success or failure. So if you are betting on a head, getting a head is success event, and getting a tail is a failure event. Okay, so that basically summarized the binomial probability distribution, 4 important characteristics. And once any procedure or any like distribution follow these 4 key aspects, we call that binomial probability distribution. And the formula for this is basically P of X representing binomial probability distribution with X amount of successes. So it's going to be n factorial over x factorial times n minus x factorial times p to the x and times q n minus x. And here, let me explain all this. You can also write it as ncx. This is a combination here, ncx times p to the x times q n minus x. And here, n is total number of trials. X is number of successes. In that flip coin case, meaning number of heads you get out of 5 trials, number of successes. We're assuming getting a head is success event, and then P is probability of success, meaning probability of a head, which is 0.5. Probability success. And then Q is probability of failure. And then here Q is equal to 1 minus P. Right here Q is 1 minus P, meaning probability of failure is a complement of a probability of success. So Q is probability of failure. Q is equal to 1 minus P. So it's what we call probability of failure. And yeah, that's pretty much all we need. And here, success or failure are neutral terms. So they are neither good or bad, right? Success, failure are neutral. It's just a relative term, but it has no real content, right? Or maybe you can say that they're just neutral. So success doesn't mean it's good, right? Failure doesn't mean it's bad. It's just your focus. If you focus on number of heads, then getting a head becomes a success event, and getting a tail becomes a failure event. So now let's look at this. Okay, so now we know the formula, how to calculate the probability for the binomial probability distribution. Now let's look at this. So let's say we still stick with the same example. Flip a coin 5 times. Find the probability of getting 0 head. Find the probability of getting, so this is part A, find the probability of getting 0 head. Again, your focus is still, it's on the number of heads, right? But here you are looking at a very extreme case of getting 0 head. Okay, so now let's take a look at how we solve it, right? So basically, in order to apply the binomial probability distribution, we need to verify this is a binomial probability distribution. So check 4 conditions, right? Outcomes in 2 categories, fixed number of trials, those 4 conditions, and also trials are independent. And then probability of success and probability of failure remain constant. And basically, we analyzed this earlier. So this flip a coin 5 times satisfy all 4 conditions. So it is a binomial probability distribution. Now, once you confirm that, then we just need to know what is n. N is 5, right? We have 5 total trials, and we know x, right? 0 head, right? Meaning we know x equals 0. And we also know p, probability of success. By default, when you flip a coin any times, you're getting 50% of chance of getting a head, 50% of chance of getting a tail. So probability of success is 50%. You can also turn it to decimal 0.5. And Q here is also 50%. You can also use 1 minus 50%, which is 50%. So they are complement. All right, so once you have all these 4 numbers available, then you can just plug into the binomial formula. So P of 0, right? X equal to 0 here is n factorial over x factorial times n minus x factorial. So this is NCX, basically its combination, and P raised to x and Q raised to n minus x. So all we have to do is just throw in all those 4 numbers. So n here is 5 factorial, x is 0 factorial times 5 minus 0 factorial. And 0 factorial is equal to 1. 1 factorial is also equal to 1. Those 2 are special case of the factorials. And P here is 0.5 raised to the x power 0 power. And Q is 0.5 as well. 5 minus 0. Okay. Now here we end up with the 5 factorial. 0 factorial is 1. 5 minus 0, 5 factorial. And 0.5 to the 0 power is 1. 0.5 to the 5th power, let's see what that is. And this turned out to be 0.03125. Okay, so now if you cancel the 5, okay, factorial, then it's gone, right? So basically you end up with 0.0. So this 1 times 1 times 0.03125, and it's 0.03125. Now I want you to try this, right? So think about same example. Now you look at find the probability of getting one hat. Find the probability of having one hat out of 5 trials. Give you a couple minutes, apply the formula, and then get the result. All right, let's go over the solutions. So here we still have 5 trials. So n is equal to 5. And then x here is one success, one hat, one success, x equal to 1. P probability of success, probability of getting hat is still 50%. Does not change. And then probability of failure, probability of getting a tail, it's also 50%, 0.5. So now again, we apply the formula. So now I'm gonna use an alternative form of formula. So P of X equal to NC X, right? So we're using combination here, and P to the X and Q n minus X. I'm gonna show you how to compute this result in Excel. So here we're looking at the probability of 1, X equal to 1. Okay. So this is 5C1, right? Times 0.5 to the X power to the first power times 0.5 raised to 5 minus 1 power. So if you simplify, it's 5C1 times 0.5 to the first and 0.5 to the fourth power. Now, I'll quickly show you how to compute this in Excel. Using the combination. Also, combination is embedded in your calculator. You can find it, and also use the combination formula to get the first part of the result. Okay. So I'm just showing you the Excel operation right now. Let me know if you cannot see the Excel screen. Okay. So first of all, we're going to calculate NCX. So you're using combination, right? So you're going to calculate the first part. You're doing combination CON, BIN. And here we have 5 trials, 5 numbers, picking one, right? Picking one head out of 5 trials. So we get a combination. And then you can multiply that by 0.5 to the first power times 0.5 to the fourth power. And that should give us a result right away. Okay, so it's 0.15625. 0.15625. So this result is 0.15625. So get that. Also, I'm gonna also show you the the other version of the formula, which is n factorial over x factorial minus x factorial. Then it's p to the x and q n minus x. Now, similarly, we bring on the numbers. So this is going to be 5 factorial divided by 1 factorial times 5 minus 1 factorial. And then it's 0.5 to the first power, and then 0.5 raised to 5 minus 1. Now from there, we're going to simplify. I'm going to show you how to do it step by step. So 5 factorial is 5 times 4 times 3 times 2 times 1. Okay. 1 factorial is 1. 5 minus 1 factorial, that's 4 factorial. It's 4 times 3 times 2 times 1. And this is 0.5 to the first power, and it's 0.5 to the fourth power. If we simplify, everything after 4 is canceled. So it's 5 over 1, 5 times 0.5 to the first, to the fourth is to the fifth power. Okay, so you can just multiply this in the calculator and get a result. The result should be the same, right? 0.15625. So definitely it's doable by hand. But if you feel like you want to use Excel to do the calculation, you can also do that. All right. And now let's just continue to just show you couple more calculation. So the third case could be find the probability of getting 3 heads. So here n equal to 5, x is 3, and then p is 0.5, q is also 0.5. Okay. And one more time, we just plug in to the formula. So p of x equal to n factorial over x factorial times n minus x factorial times p to the x times q n minus x. So one more time, we just plug in the numbers. 5 factorial by 3 factorial times 5 minus 3 factorial times 0.5 to the third power, and then 0.5 raised to 5 minus 3, which is 2, right? Then again, let's simplify. 5 factorial, 5 times 4 times 3 times 2 times 1. 3 factorial, 3 times 2 times 1. And this 2 factorial is 2 times 1. So one more time, we could cancel something, right? So 3, 2, 1, we can cancel that. 3, 2, 1. And on top is 5 times 4, 20 by, on the bottom is 2, 20 by 2 is 10. So this is 0.5 to the third and then 0.5 to the second. If you combine them, this is 0.5 to the fifth. So it's 10 times 0.5 to the fifth. And let's get the result. It should be the double of the previous one. So 10 times 0.5 to the fifth. It's 0.3125. This one actually has the highest probability, right? 0.3125 among all those different outcomes. Let's just look at another extreme case, right? Let's say you want to find the probability of getting exactly 5 heads. Find the probability of having 5 heads out of 5 trials. So n equal to 5, x now is equal to 5 heads, 5 successes, p is 0.5, q is 0.5. So apply the formula one more time. And this result will be the exact same thing. Having 5 heads and having 0 head will have the same result. We'll see that in a second. 5 heads, 5 tails are equivalent outcomes. Okay. So here we get a px n factorial over x factorial times n minus x factorial. And this is p to the x and q n minus x. And throw in the numbers, 5 factorial by 5 factorial, 5 minus 5 factorial, 0.5 to the 5th power, and this is 0.5 raised to 5 minus 5, 0 power. And to simplify, on top is 5 factorial over 5 factorial. This is 0 factorial is 1, and it's 0.5 to the 5 times 0.5 to the 0. Any number raised to 0 power is 1. And 5 factorial cancel 5 factorial. So first part of the result is 1 times 0.5 to the 5th times 1. And 0.5 to the 5th, exactly 0.03125. 0.03125. I can also quickly show you how to get it in Excel. So here still combination, COM, EIN. So we have 5 trials. We picking 5 heads out of 5 trials and multiply by 0.5 to the 5th power times 0.5 to the 0 power. And that should give us a result. Right? There you go, it's 0.03125. And you can easily verify that. So any question on this example? So basically, when you flip a coin 5 times, right, you have 5 possible outcomes, either getting 0 head, 1 head, 2 head, 3 head, 4 head, and then 5 head. And so that's basically 6 outcomes. So you have all those 6 outcomes, and you'll be able to use a binomial probability formula to calculate all those probabilities for each associated outcome. Now let's take a look at another example. Okay. In the old days, meaning in the 1920s, 30s, something like that, that was a probability of 0.8 or 80%, right? 80% of chance, 80% of chance in any attempt to make a phone call. And calculate the probability of having 7 successes in 10 attempts. Calculate the probability of having 7 successes out of 10 trials in 10 attempts. Give you a couple minutes, think about this, how to solve it. Okay, so let's go over this. Does anyone want to share your answers on this or how to solve this? Anybody want to share your answer? Okay, I guess not. All right, no problem. So think about this. It looks like a binomial probability distribution. So, but first of all, we got to verify that. So here we need to check all those four conditions. First one is outcomes in two categories, right? If you look at each individual attempt, you either successfully make a phone call, right? Or you fail to make a phone call. So here, the first condition is satisfied. Outcomes in two categories, either success or failure. Two categories. Success or failure. Okay. The second one is outcomes fixed number of trials, right? Here, remember, we only have 10 trials, 10 attempts, fixed number of trials. In this case, n equal to 10. And third condition is trials are independent. Definitely, they are independent. Getting a success in the first one of the 10 does not guarantee you end up with another success. Okay, so trials are independent. And also, fourth condition is probability of success and probability of failure remain constant. So here, probability of success is always going to be 80%, right? 80% chance to make a phone call. Probability of success remain constant. P equal to 0.8, 80%. So once you verify these four conditions are satisfied here, so then we know that it's binomial distribution, probability distribution. And we can apply the binomial formula to get a result. So P of x equal to n factorial over x factorial times n minus x factorial, and p to the x and q n minus x. So we just need to know what is n. N is 10 trials. Number of successes, we want 7 successes, 7 successes out of 10 attempts. Right? And probability of success is 0.8, probability of failure is 0.2. P equal 0.8, Q equal to 0.2. Okay. And once you have all those four numbers ready, then plug into the formula. So P of x equal to 7 here should be 10 factorial over 7 factorial times 10 minus 7 factorial multiplied by 0.8 to the 7th power, and then 0.2, Q is 0.2, its complement is 10 minus 7, which is 3. If you do it by hand, you see the factorial is kind of large. Definitely you can do it by hand, no problem. I can work it out with you. So 10 factorial is 10 times 9 times 8. Okay, so it's just expanded. And 7 factorial will be 7 times 6, 5, 4, 3, 2, 1. Okay. We know that we will cancel all of that. And then 10 minus 7 is 3 factorial. So it's 3 times 2 times 1. Okay. So everything after 7.
Professor, I have a question.
Yeah, sure.
How did we get P equals 0.8 and Q equals 0.2?
Okay. So here, P represents probability of success.
Mm-hmm.
So you have 80% of chance in any attempt to make a phone call. So 80% is the probability of success.
Oh, okay. It was in the question. Thank you.
The question, yeah, exactly. So the probability of failure, so meaning you have 20% of chance of failing to make a phone call, right?
Yeah, that makes sense. I just didn't see it in the question. Thank you.
No problem. Okay, so we have that here. So we cancel everything after 7. Right, so that's gone. And we can simplify this. 3 going to 9, that's 3 times. 2 going to 8 is 4 times. So it's 10 times 3 times 2, 4, which is 120. And this is 0.8 to the 7th power and 0.2 to the 3rd power. So it's 120 times 0.8 to the 7, 0.2 to the 3rd. Okay. Okay, I'm going to show you how to get it done in Excel really quick. So if you do 120 times 0.8 to the 7th power times 0.2 to the 3rd power, so we get a result, right? That's it. And also I'm going to confirm this using the combination formula. So combination, we have 10 trials, repeating 7 success out of 10 trials, multiplied by 0.8 to the 7th power, multiplied by 0.2 to the 3rd power. Okay, and we should get the same result, right? Yeah, exactly the same thing. Okay, so using combination formula, it's quicker. You don't have to perform any operation in original question. We do not want to do that. Yeah. Okay. And this is binomial probability distribution in chapters 5. And I think that's pretty much everything from chapter 5. And I will also want to get started on chapter 6, just start a little bit on the chapter 6, give you some introduction on the normal distribution and uniform distribution. So chapter 5 will deal with a discrete random variable. So this is still discrete random variable, right? Meaning we're talking about finite countable, right? And countable random variable. And usually we're looking at the numerical numbers. Here they're all numerical numbers in terms of the number of successes, right? Either 1 or 2 or 3 successes. And starting on chapter 6, we start looking at the continuous random variable, so which is a lot more complicated compared to discrete random variable, and has a lot more applications in the real world. So chapter 6, normal distribution.
Will we review this after we take the midterm?
Oh no, chapter 6 is not in the midterm.
Yeah, but will we review what you're teaching us now?
Oh, you mean after the midterm? Yeah.
Okay.
I'll just do a brief introduction today, and we'll continue talking about this topic. I'll give you some time to finish your Excel project number 3. Today, after I introduce the normal distribution and uniform distribution, right? And starting on this chapter, we focus on the continuous random variable. It's slightly more complicated compared to the discrete random variable. There's a lot more applications in real world. So continuous random variable is basically a random variable has infinitely many values. Usually appearing in the interval without a gap. In the interval or in the range without a gap. Like I think the good example could be number of gallon milk a cow produces in a given day, right? That's usually a continuous random variable. So it's anything between 2 gallons to 3 gallons, and any number in between are possible. So we have infinite many numbers are possible in between that 2 gallon, 3 gallon interval without a gap. So this one sentence summarizes what is a continuous random variable. And typically the graph of this continuous random variable will look like this, right? Something like it's happening on a continuous scale with an upper bound and lower bound. So that's the interval we're talking about. And if you look at the stock market, actually behave very similar compared to this, because it's what we call a continuous random variable, right? The stock price or any like index price. So you just go up and down, and it's following a particular interval. Okay, that's what the continuous random variable look like. And if the continuous random variable follow a distribution look like this, if a continuous random variable has a distribution that is first important characteristics bell-shaped. Second important characteristic symmetric. Symmetric with respect to center, with respect center of the data set. We call this, and this is, it's called normal distribution. This is a formal definition of the normal distribution. And graphically speaking, we're looking at something like this. So this is what they call a bell curve. And bell curve just summarize the location of each data values, right? So basically, you have different data values, and this is the center. Center is right in the middle. The center here we can also call the interesting thing about a normal distribution is for normal distribution, the center has the same location of the mean, median, and mode. And usually for a given data set, that doesn't happen all the time, right? It's the mean, median, mode usually are not the same number, right? If you just look at any data set, but for normal distribution, mean, median, mode, they're all the same. So mean is just, so the center, you can use mean, median, mode to represent the center. And center is right in the middle. And this bell curve is symmetrical with respect to the center, meaning this is the probability distribution. So the total probability under the bell curve is 100%. So this center will split the bell curve into half and half. So meaning on each half, it's 50%. Which means that 50% of data is below the center, 50% of data is above the center. So this center is very crucial, right? It's split half and half, and then create a symmetrical image here based on the center. Okay, so this is important thing about center. So it's bell curve first of all, it's bell shaped, and also symmetrical with respect to the center. And the total probability under the bell curve is 100%. because it's a probability distribution. So from chapter 5, we know that for probability distribution, total probability is always going to be 100% or 1. So, and also, if you look at the bell curve, it basically gives you the distribution of all the data values. So meaning, let's say we have a sample size is equal to 100, right? If I have a sample size of 100, that means 50 data will be here. According to the bell curve, 50 data will be below the mean, 50% of 50 data will be above the mean. Okay. Sample size is 100. And that just gives us a distribution of the data values. And then we could be more specific once we implement a mechanics called z-score, right? And z-score will basically show us for any given data value, the location of that particular data value. Okay. And then you're going to see that in a second. But in terms of bell curve, the formula we utilize to summarize this bell curve, remember for linear equation, we're using the straight line, we're using linear equation to represent it. We have quadratic equation, we're using the quadratic formula, right? And here, the formula to represent this bell curve is this f of x. It's very complicated. You don't have to memorize any of this. Just want to show you what this look like. X minus mu square over 2 sigma square. Okay. Dividing by sigma times square root of 2 pi. This is the function we utilize to representing this bell curve. Here we know mu is the population mean. Sigma is population standard deviation. And we also have a couple important things here. E is it's Euler number. E is natural number. E is approximately equal to 2.718. Right, and just like pi is approximately equal to 3.1415196, right? It has infinitely many decimal places. Those two are very, so basically X represents a continuous random variable, and this is the formula to represent this, the bell curve. But again, just know that's a formula, used for the bell curve, but you don't have to memorize any of this. Now you focus more on the application of this normal distribution. Okay. And next thing, let's take a look at this standard normal distribution. So standard normal distribution is a special case of the normal distribution. So for the standard normal distribution is a normal distribution with mean equal to 0 and standard deviation equal to 1. It's a normal distribution with mean equal to 0 and standard deviation equal to 1. So this is important thing about this standard normal distribution. So now if you look at the z-score formula, x minus b over sigma. So here for the standard normal distribution, mu is equal to 0, sigma equal to 1. So if you throw in both numbers into the formula, so the z-score is equal to x minus 0 over 1. And x minus 0 is x over 1, and just become x. That means z-score is the same thing as the given continuous random variable for the standard normal distribution. And that's kind of important. Also, it's kind of useful. That means anytime if they give you the continuous random variable, like let's say temperature, something like that, and that actually becomes a that actually becomes a z-score. So now let's take a look at this example. Let's see how we apply this standard normal distribution. Let's assuming a scientific thermometer. Scientific thermometer. To show 0 Celsius. 0 Celsius at the temperature that water freezes, right? For the freezing point. The temperature water freezes. Assuming mu equals 0 and sigma equal to 1. Find the probability that for a thermometer the temperature shown is below temperature. Let's do this. The temperature shown is below 1.58 Celsius. Okay, so basically this thermometer, scientific thermometer follows standard normal distribution because mean equals 0, standard deviation equal to 1. And first one, you want to find out the probability that the thermometer, for another thermometer, they measure the temperature and the temperature shown is below 1.58 Celsius. So basically you just draw a bell curve, right? Anytime you see the standard normal distribution or normal distribution, draw the bell curve first and label the center. Center here, mu equals 0. Okay. And then 1.58 Celsius, this is a given temperature, right? It's on the right-hand side of 0. So this x is equal to 1.58 Celsius. Yeah. Okay. And then the key language here is below, right? Below meaning you want to look at probability accumulate all the way to the left. So you want to accumulate the probability all the way to the left of temperature of 1.58 Celsius. Okay. This is what the question is asking you to do. So first of all, in order to find out the probability, we need to know the z-score. Okay. So using z-score formula, x minus mu over sigma. Here x is 1.58 as targeted temperature, mu equals 0, and sigma equal to 1. As I mentioned, if you throw in all the numbers, the z-score will become the temperature itself. So it's 1.58 minus 0 over 1. And this turned out to be 1.58 over 1. And this turned out to be 1.58. And the z-score is the exact same thing as the temperature itself. And this is a very useful feature of the standard normal distribution. And here x equal to that, z-score is the same thing, 1.58. And I'm going to show you the table we are utilizing to find out the probability, right? So z-score is like the middleman, right? So z-score connecting the probability associated with any given data value. So if you go to the Blackboard, open the formula sheet, and we're going to start looking at the first table. which is table A3. So open, go to our course. Then let's open the formula sheet. And we go all the way down, we pass all formulas, you see the table. And the first table you see will be the table A3, I believe. Yeah, table A2, right? Table A2. So in the table A2, anytime if you know the z-score, then you'll be able to find out the probability or the area to the left-hand side of that corresponding z-score. So for example, for this temperature case, the z-score is 1.58. So if you know the z-score 1.58, you'll be able to find out probability associated with the accumulation of all the area to the left-hand side of that z-score. So in this case, there's negative z-score here. First page is all the negative z-score. The second page is all the positive z-score. And the z-score we have is 1.58, which is positive. So go to the second page of table A2 and look for 1.58. And you'll find the corresponding probability, right? So this corresponding probability turned out to be 0.9429. So on the Z table, 2 elements, the whole number, 10th digit, it's located on the first column, and the second digit, the 100th digit is located on top, right, on the top column. And they're gonna have intercept, and intercept is what we call the probability we're looking for. So again, the table only gives us probability to the right-hand side of that z-score. It doesn't tell us the right-hand side, right? So only the left-hand side, and the left-hand side is what we're looking for. So the probability we're looking for here is 0.9429. Okay, this is 1.58. Okay. So go back here. The answer for this problem will be all the probability to the left-hand side, it's 0.9495. It's 9429.
I have a question.
Sure.
So the reason why you did 1.5 and 0.08 was because the number was 1.58.
Right, the temperature is 1.58 Celsius.
So like the ending like decimal number.
So here the temperature representing the continuous random variable, right? Remember the temperature could be a random number between, let's say, the high temperature, on Earth, maybe it's negative 50, negative maybe 80 Celsius all the way to 60 Celsius. That's the interval. So any temperature in between are possible. And in this case, we're looking at the temperature below 1.58 Celsius. So this 1.58 Celsius becomes a random variable, just continuous random variable. And it follows the standard normal distribution because mean equals 0, standard deviation equal to 1. And basically you're going to converting this temperature into a corresponding z-score, because z-score tells us the location of this temperature in terms of the compared to the other temperatures. So, and z-score, basically we compute it using the z-score formula. And you also learn it from chapter 3, remember it's the same concept. You're using z-score to measure the relative standing of the data value. And here the z-score turned out to be 1.58. And the z-score is like the bridge. You're connecting the actual temperature to the probability. So now the table A2 is what we utilize to find out the corresponding probability here. So when the z-score is 1.58, you see 1.5 is here, 0.08 they're gonna have intercept, and the intercept is a probability you're looking for. Okay. See that? So this probability turned out to be 0.9429. That's all the areas accumulating to the left. Does that help? Okay. Yeah, so what this tells us is, if you go back a little bit, meaning 94.29% of data, right, fall in this particular range, fall in this, so this temperature is basically with the occurring with 94.29% of chance. So below, the temperature below 1.58 Celsius will be 94.29%. If you convert percentage, it occurs with this percentage, with this probability. Meaning if you have a, let's say, 10,000 temperatures recorded, right? In this particular case, that means 10,000. So that means 9,429 temperatures will be located to the left of this particular temperature. So that's how we interpret this probability. We calculate using the table. It's giving us idea of relative standing of this temperature, also all the temperature below it. Okay. Any other questions on this? Okay, let's look at this. Find the probability that temperature shown. Find the probability that temperature between negative 1.25 Celsius and then 1.75 Celsius. Okay. So now you're looking at the in between. Okay. So temperature in the middle is 0, right? It's the freezing point. So you equal 0 in the middle. So now you're looking at negative 1.25 Celsius on the left of the 0, and then 1.75 is on the right. And you're looking at the temperature, the probability, right, associated with those two temperatures. The probability between those two temperatures. Okay. So first of all, you want to find out z-score associated with the higher temperature, 1.75. And if you apply the formula one more time, z-score will be the same as the temperature itself. That's because mu equals 0 and the sigma equal to 1. That tells us x minus mu over sigma will be the same as the temperature itself. So 1.75 minus 0 over 1, that turned out to be 1.75. That actually tells us that the z-score here for this particular temperature is 1.75. And similarly, the z-score for this temperature here will be negative 1.25. And we cannot get to the probability directly. So we need to use the z-score to find the probability. So now if you look at the z-score of 1.75, so you always use the bigger z-score first, and then go to table A2. Now if you go to the second page of table A2, just use this. Yeah. And you look for 1.75. So here we go 1.75 here. 0.9599, right? I'm gonna use a different color here. Okay, look at that. So this is the corresponding probability associated with a z-score of 1.75. That means we're talking about everything to the left, right? All the area to the left of 1.75. And so this is a bigger z-score. It gives us a bigger probability. And then the smaller one is negative 1.25. So negative 1.25 here, negative 1.25 give us a probability of 0.1056. And still we're looking at the area to the left hand side of that. Let me just highlight it on pink color. So this probability is 0.1056, and then the bigger probability is 0.9599. So if you go back here, so the probability associated with the z-score equal 1.75, we include the designated area in between, also this triangle area here. All right, and this is 0.9599, right? Which is the bigger probability. And then the area to the left-hand side of z-score of negative 1.25, it's 0.1046. And double check. Yeah, 1056. Right. This only captured the area to the left-hand side of that z-score. If you go back here, it only captures the triangle area. And then if you want an area in between, you find a difference between those two areas because the triangle area can offset each other. So you end up with the 0.8543. That means the area in between those two, the designated area is 0.8543. This means 85.43% of the data falling the area in between. Right? And also you can say that the probability for the temperature between negative 1.25 Celsius and 1.75 Celsius, it's 85.43%. So give us an idea, how many data value fall in that interval. Any question on this? This is in between case, right? What if you want to find out the area which is above? Find the probability. The temperature shown is above 1.56 Celsius. Okay. Now this is third case, which is above indicating it's bigger than 1.56 Celsius. So the bell curve mu is equal 0. Now we know that temperature equal to 1.56 should be on the right hand side of the center. And then here we're talking about area to the right hand side of this particular temperature. And using a z-score formula, we know the z-score will be 1.56. You can use that to find the area to the left. And we know that total area under the bell curve is 100%. Total area under the bell curve, 100%. If we know the area to the left, then we'll be able to find out the area to the right. Now still go to the table A2. Look for 1.56. It's on the second page. 1.56. and the corresponding area is 0.9406. Here we go. So this 0.9406 is the area we're looking for, which is on to the left. Maybe go back 0.9406. That means we know the area to the left is 0.9406. However, we want the area to the right, this area here. And the total area is 1, so we're using 1 minus 0.9406. This turned out to be 0.0594, which means 5.94% probability. Also, another way of interpreting this is 5.94% of all the data values will be above 1.56 Celsius. Okay. So this is give us idea the distribution of all data values. And we went over all 3 different scenarios: below, above, between, in between. And that's all 3 cases you can encounter, right? In terms of dealing with a standard normal distribution. Okay. And something I really want to mention one more time. So before next Monday, I really want you guys to try the midterm exam review, right? You should definitely try yourself first. It's available now. You can try it as an assessment of how you did in the first 5 chapters. You also get a better idea what will appear in your actual midterm exam. The question will be similar to the midterm exam review. So if you do well on the midterm exam review, that means, yeah, you're ready for the actual midterm. Okay. But definitely try yourself, and then you work on it first, and then I went over the solution, and actually you get a better feedback, right? You also get more out of the review session. Okay. So many of the time I'm put you in a breakout room, and then you can finish the Excel project number 3, right? If you finish that already, I probably finished grading that already. So if you want me to give you feedbacks, right? Where you made a mistake, let me know. I can talk to you during the breakout session and give you some instruction. Any questions? Okay. So you should finish the project number 3 today, right? If you haven't done so, if you finished already and have no other question, feel free to go. Okay. And next Monday, we review for the midterm exam. Hey, Kiara.